Okay, it's exam 2 for spring 23. We had capacitors and resistors in series and parallel, no multi-loop circuits, no home circuits, no RC circuits. First circuit, the first thing that you want to do is redraw it so that it looks more like what we have. Notice as I come up here, I haven't gotten a junction by the time I get to C1, so I'm going to draw that as just a 2 microfarad capacitor. But notice here that I have a junction that splits into 1, 2, 3 branches. So let me tidy this up just a little bit. There's our first capacitor. This is 12 volts right here. And then I split into 3 branches. And we'll do this as the top branch. C2 is 2 microfarads. And then I have a 9, a 9, and a 9 in series, which isn't a combination we've seen before, but we'll see that it's pretty simple. And then I have a 1 microfarad down here. And then these are 9 microfarad. And then notice here that all of these, I can count all of these junctions as 1 because there's no electrical devices in between them. So it's like I can combine this point with this point with this point. Those are really the same point electrically. So I get another junction with 3 branches in it. On top, I have a 2 and a 2. I have a 1 and a 1. And then it comes back over here and it goes back to the battery. Let's see, this was a 2, a 2, a 1, and a 1. So you probably want to do this first thing, just redraw it so that it looks more like what we've been working with, and then you can identify the parts that you want to simplify. And so here we're going to simplify these two. That's 1 over 9 plus 1 over 9 plus 1 over 9. That's 1 over a third, which is equal to 3. So I'm going to replace that with a 3 microfarad capacitor. And then the 2 and the 2 is 1 over a half plus a half, which is 1 over 1, which is 1. You know, let's go ahead and, no, I'll redraw this actually. Let's see. Just for sake of time, I'm just going to write the numbers here, 2, 3, and 1. I'll go and write the units. I'm trying to hurry. I shouldn't hurry. We have plenty of time. Actually, these should be just a 1 microfarad. You're probably starting to see how this is going to go. I have a 2 and a 6 and a 3 all in series with one another with a 12-volt battery. 2 microfarads, 6 microfarads, and 3 microfarads. And then I can do the sum of these. So you might remember that 1 over 2 plus 1 over 6 plus 1 over 3, that's equal to 1 over 3 plus 1 plus 2 divided by 6. That's 3 6 plus 1 6 plus 2 6, which is 6 over 6, which is equal to 1. So the equivalent of this circuit, see, I'm going to go back to blue. The equivalent of this circuit is a 1 microfarad capacitor with 12 volts. That means that I have 12 microcoulombs of charge on that capacitor, which means I have 12 microcoulombs over here, 12 microcoulombs here, and 12 microcoulombs here. So if that's my charge, then I know that the V is equal to Q divided by C. That's 6 volts, 2 volts, and 4 volts. Let's just pause here and double check this. I have 6 plus 2 is 8, plus 4 is 12. And then also notice that this voltage is 3 times this voltage. And this capacitance is a third that capacitance. And then this voltage is half this voltage, and this capacitance is twice this capacitance. So everything sits as it should in the proportions of these various voltages, and they all add up equal to 12 as they should. So I can go back and assign these voltages to, well, these capacitors here in parallel, because I know that capacitors in parallel have the same voltage. These have 4 volts, 4 volts, and 4 volts. And then I can go back and, well, let's see what I'm looking for. I'm looking for the voltage on C1. I already have that. That's 6 volts. I'm looking for the voltage on C6. That's that. And C6 is this capacitor, so that's that. And then I'm looking for the charge on this capacitor. Let's see, where is that? That is, one of the, excuse me, one of the equivalents of this one. So it's going to be this capacitor up here, which has, I know, 2 volts. Because this one had 4 volts, this one is half, and it's identical to this one, so it splits that voltage evenly. So it has 2 volts, and then 2 times 2 is 4 microcoulombs. So that's going to be 4 microcoulombs. So those are the numbers that I was looking for, but I really also need to see your work as well to find the charges or voltages on each of those capacitors. Here, let's look at this circuit. I know that I can combine these two resistors. It gives me that voltage, and then I can combine these two. 1 over an eighth plus an eighth is 1 over 2/8, 1 over a quarter, or 4. So I can combine these to give me 4 ohms. And I'm going to go and combine these two, which would also give me 8 ohms. So I'm going to redraw that now. Let me show you what I got. I have a parallel branch with an 8 ohm up here, and a 4 plus 4 are 8 ohm here, and 4 ohm there, and 16 volts there. And then I've already done that 8 and 8 in parallel, so I know that's 4 ohms and 4 ohms, which is 18, excuse me, 8 ohms with 16 volts. So the equivalent resistance is right there. Let's go ahead and find the current. So the current here is V over R, which is 2 amps. Means I have 2 amps here. 2 amps there, which means that I have 8 volts and 8 volts. 2 times 4, 2 times 4, but you probably knew that because I had 16 volts and it's split in two by those capacitors, excuse me, resistors in series. So I have 8 volts here, and I also have 8 volts here and here. I have 2 amps coming here. That 2 amps is going to split into 2 identical currents of 1 amp and 1 amp. Now let's just answer what I have here. So R2 is the same, or is the one of the component resistors of this. So a 2 and a 6. Now I know that these have 1 volt, excuse me, 8 volts across them. I know that they have 1 amp going through both of them. That means that the voltage across R2 is going to be 2 times 1, I times R, or 2 volts. And then the current through R4, let's see, I know that I have 1 amp coming here, right? That was the current here because I have 8 volts, 8 ohms. That 1 amp, well, gosh, I can just say that it splits evenly here because I have 2 identical. So I'm just going to say that it has 0.5 amps because that current splits identically through those 2 resistors. Okay? All right. Let's go on to number 3. Here, what is the resistance of this wire? Well, R is equal to rho L over A. That is, let's see, let's go to number 11. I'm looking for copper, 1.7 times 10 to the minus 8. Is that right? Yeah. I have to get the resistivity of that copper. the length is 0.0011 meters, and the length, excuse me, the radius is 0.0111. The length is 0.5 meters, and the area is going to be pi times the radius squared, 0.0011 squared. Let's see, that gives me I get 2.2 times 10 to the -5 ohms. Right, this is just a piece of wire. It basically has no resistance. Or wait, no, -5. Excuse me. It basically has no resistance at all. And then I want to know what is the power. So that's A. Well, there should be very little power dissipated in this. I know that a battery provides 6 volts of potential. I know that power is equal to V squared over R. Let's say there's very little power. Actually, because it has such a low resistance, it's going to have a very high current. It's like shorting a battery, and so it's going to have a high current, which is going to dissipate a lot of power. So that's going to be 6 squared over this 2.2 times 10 to the -5 ohms. I get a 1.6 times 10 to the 6. 1.6 times 10 to the 6 watts, or you could report it as 1.6 megawatts. All right, let's go to this. I have a capacitance, capacitor C. You double the area. Let's just go ahead and write down this epsilon naught A over D. If I double the area of the plates and make the separation 1/2 of what it was originally, 2 divided by 1/2 is equal to 4. So I'm going to get 4 times the capacitance, because doubling the area of the plates, that increases the capacitance, and moving them closer together also increases the capacitance. Here, I just want to calculate the capacitance. C is equal to kappa epsilon naught A divided by D. That kappa is 1.5. Epsilon naught is on your equation sheet. That's in farads per meter, I think. And A is given there. Oop, sorry, that's distance. I keep getting those mixed up today. Y'all don't do that, okay? A is 0.2, and then 3 times 10 to the -6. See, if I do those calculations, I get the answer. Well, let's see, I can cancel this with this to give me 0.3, and then that to give me 0.1. So that's 0.885, 0.885 times 10 to the -6 farads, or 0.89 microfarads is the right answer. What is the charge on the 4 microfarad capacitor? Well, let's simplify it. I have a 3 microfarad and a 6 microfarad in series. I know that these two are going to carry voltages. This one will carry a small voltage, this one a big voltage, that add up to equal to 12. They're twice the other. And so the charge, the voltage then on this one will be 4 volts, and 8 volts. So the charge on this one is going to be Q equals C times V, or 16. 3 is E. All these capacitors are identical. What is the voltage provided by the battery? Well, I know if this one has 16, this one also has 16 volts, and I know that that would be a capacitance and a twice that capacitance. So I have a capacitance here and a 2C here. The capacitance is twice what it was. Let's see, sorry about that. So if I have these separation of the capacitors or distribution of the capacitance, and I want to know what the voltage is here. Well, look, I know that this has 16 volts. This capacitance is half this capacitance. Hold on. So since this is 16 volts, excuse me, since this is 16 volts, because that was what I had on these two capacitors, then I must have 32 volts here, because I have to have a voltage that's twice that of the bigger capacitor. And then 32 plus 16 is that. Measure voltage of 6 volts, resistor of 3 ohms. I just want to know how much charge. I is V over R. That's 2 amps, and Q then is going to be 2 amps times 5 seconds, or 10 coulombs. C is 5. Which of these statements is necessarily true? Okay, that one's true. Um, this one is also true, that the voltage across an ammeter is very small because it has a very small resistance. So it has also a small voltage. Remember, you want to not affect the device or the circuit that you're measuring. So you don't want the ammeter to have a big voltage drop. The resistance of an ammeter is small, that's true, and the current through a voltmeter is small, that's true too. This has not a small resistance, but a really big resistance, and so it's not going to allow for a very big current, a very, very small current, in fact. So all are correct here. Electric oven operates at 240 volts and it draws a current of 60 amps. I want to know what is the resistance. The resistance is V over I. It's 240 over 60. That's equal to about 4 ohms. So a very low resistance. Here, looking at this graph, which notice this graph has a slope equal to 5 divided by 20, which is 1 over 4. I want to know what is the value of the resistor. Well, I know that I is equal to 1 over R times V. That's what I've plotted here, I and V. So this represents the slope, which is, excuse me, not that. Uh, Solve that for R, so it's equal to D is the right answer. You consider these three circuits, rank the four bulbs, A, B, C, and D, from the brightest to the least brightest. Well, let's say that this is 12 volts and 12 volts and 12 volts. And I would have 6 volts, 6 volts, 4, 4, and 4. Here I'd have 12, and then I'd have 6 and 6. So notice that D is the biggest. It's the brightest. The brightest. Remember, power is equal to V squared over R. They all have the same resistance. So the one with the biggest voltage is going to have the biggest power. The next biggest is going to be A or C. So this must be the right answer right here. A is equal to C, and then B is the smallest voltage. Wire's resistance R. You make a wire of the same material but with a diameter 4 times bigger and a length 4 times longer. So let's remember what this equation is. R is equal to rho L over A. I'm quadrupling the length and the diameter is 4 times bigger. That means the area is 16 times bigger. So I have a 4 over 16, or C is the right answer. Let's see here, I want you to calculate the resistivity. First, we have to find the resistance. That's going to be 10 divided by 5, or 2 ohms. And then I know that R is equal to rho L over A. So I solve that for rho. RA over L. That's 2 times the area divided by the length. Also, it's 1.7, so A is the right answer. Notice these cancel, and I'm left with that number. What happens if you remove R3 and replace it with a wire? What happens to the voltage across this? Well, let's think about this. So let's just think about what the numbers are. Well, no. Let's think about it. If I remove that resistor, that means that the resistance of this part goes up, which means the voltage of this part, excuse me, I'm sorry. If I remove R3, that decreases the resistance of the overall circuit. The overall circuit will go down. When I remove resistors in series, it decreases the equivalent resistance. So if R goes down, that means that the voltage is going to go down. If you're not sure about that, let's just, I mean, we've done this before. Let's look at these. The numbers are fairly simple here. So let's just look at that. So here I would have 3, 6, and 2 ohms, uh, which is a 2 and a 2. So that means I'm going to have voltages of 6 volts over here, 6 volts, and 6 volts. All right, but what happens if I take this one out? Then if this one goes away, that means I have 12 volts here and 12 volts here, which is the opposite of what I just said, isn't it? Yeah, I'm sorry, y'all. It's a good thing I checked it, right? So if I take this out, the overall resistance goes down. So that means that the current goes up. So the voltage across those, or really if I was thinking about it, if I take this away, then all of this 12 volts is going to go onto those two resistors. Sorry about that. All right, let's assume all three resistors are in the circuit. What is the current in the 3 ohm resistor? Oh gosh, didn't we just find this? So where's the 3 ohm resistor? Well, if I have, this is my 3 ohm resistor right here. Have 6 volts, we decided, right? Because the equivalent of this is a 2 ohm resistor. That means I have 6 volts, 6 volts, and 6 volts. So the current through R1 should be I is equal to V over R, 6 over 3, which is 2 amps. Okay, I don't know what happened here. Let's get rid of this stuff. I want to know if bulb A has a voltage of 6 volts, what are the voltages of bulb B and bulb D? And notice that the voltages here are all the same, which means that this has to be 12 volts, which this is 2 and this is 2. Um, and if that's 12 volts, that means that this is 4 volts, and that means that this is 6 volts, and that means that this is 12 volts. I'm just looking for B and D, so that's going to be 4 and 12. What is the total current in this circuit? These two resistors in parallel have this equivalent resistance. So that means that this current is, which is C. Which of these rules are correct? That's not true. I can make it true by saying this. That's not true either. I could make it true by making this into current, perhaps, or I could say make this into series, but as it's written, it's not true. This is not true either. I can make it true by writing this, and that is not true either. Is always smaller than the smallest. So E is the right answer. Which of these are true? That's not true. It would go down, in fact. That's not true. Could be if they're all zero, if they were all in infinite resistance, I suppose. Um, that is true, and that is true. All right, so D is the right answer. What is potential across the 12 ohm resistor? Look, the equivalent is 24 ohms. So that means I know that I have 0.5 amps in each of these. Right? I is 12 divided by 24. So if I want to know the potential across this one, 0.5 times 12 is 6. Here it would be 4 and 2. I could add those up and find that they equal to 12. What is the voltage provided by the power supply? We did a one similar to this. Let's see. So if this is 9 ohms, that means that this one's going to have a third of this one. So it will have that voltage. So the total voltage is there. Now let's see. All these are really awesome students, but E is the right answer. Okay? All right, good job.